let's find another power series with the geometric power series, using some known functions. But I want to do this in two separate ways because there's some interesting things that you can learn from doing it both ways. So first is, okay, we got 16 over 9 minus x squared, and I want to find a power series centered at c equals 0. So the way we do this is the way we do everything else. We say, all right, I want to do, let's not worry about that x squared. Well, I mean, we're going to worry about it, but it's just going to be absorbed into our r. So sometimes you might just want to focus on the x, but we'll just leave x squared as normal. So I have 16 over 9 minus x squared. Now what I need is I need this to be a 1. It's got to be a 1. So the way we do that is we factor out the 9. Like that. Then we rewrite that as 16 over 9 for 1 minus x squared over 9. Right? So you write it like that. This becomes a. This becomes r is x squared over 9. So then we write that as the power series from n equals 0 to infinity. 16 over 9 times x squared over 9 to the n, which you might want to write instead as n equals 0 to infinity, 16 over 9, x to the 2n over 9 to the n. Either one of those is fine, not a problem. Now we need to find the interval of convergence. This one's going to be a little trickier because we have to say, all right, this thing, the magnitude of this has to be less than 1. So the magnitude of x squared over 9 has to be less than 1. Now here's the thing. This thing's always positive. X squared over 9 is always positive. So now I have x squared over 9 is less than 1. So x squared is less than 9. So if x squared is less than 9, then I could have negative numbers that come to 9. I could have positive numbers that come to 9. So that tells me that it goes from negative 3 to positive 3, right? Because I can plug negative numbers into there to get that. So my interval of convergence is negative 3 to 3. And that's my power series. Okay, simple enough. And that's probably the right way to do that. But I'd like to do this, if you want to watch a little longer, I got to add another half a board. I'd like to do it a separate way, a way that involves technique that hopefully you're familiar with, the idea of partial fraction decomposition. So notice that this is 16 over, here, I'm going to write this as negative 16 over x minus 3 x plus 3. And hopefully you can see that factors because this is a difference of squares, but this is actually x squared minus 9, so I have to take a negative to do it. I have to do some algebraic manipulation, right? So then that gets me some sort of a over x minus 3 plus b over x plus 3. So then I multiply both sides by x minus 3, x plus 3, and I get negative 16 is a times x plus 3 plus b times x minus 3. So then when I plug in like negative 3 for x, what I get is that this disappears. Negative 6b is negative 16. So b is 8/3. And that's going to tell me a is negative 8/3. Why am I doing this? Okay, well now, why am I doing this? Well now, what I have is negative 8/3 over x minus 3 plus 8/3 over x plus 3. And then I actually need to negate these again, so I probably shouldn't have done that. This is going to be 8/3 over 3 minus x plus negative 8/3 over 3 plus x. at which point I have to factor the denominators to get 8/3 over 3, 1 minus x over 3, plus negative 8/3, 3, 1 minus x, or 1 plus x over 3. So what I actually get is 1 minus negative x over 3. So then I can pull that to the top. I get 8/9, 1 minus x over 3, plus negative 8/9, 1 minus negative x over 3. So now I have these in the form I'm looking for. I have it in A, 1 minus r, A, 1 minus r. So I get two power series here. I get power series n equals 0 to infinity of 8/9 x over 3 to the n, plus n equals 0 to infinity negative 8/9 negative x over 3 to the n. So now I actually have two power series that I have to contend with. So there's a couple, and we can actually combine these even further, because I can do this. I can say, well, that's technically this right here, and instead of negative x over 3, here, we'll leave that here. That's actually x over 3 to the n times negative 1 to the n. Alright, so then I can say that this is 8/9 n equals 0 to infinity x over 3 to the n, plus 8/9 n equals 0 to infinity negative 1 to the n plus 1, because I get that negative plus that, times x over 3 to the n. So now notice I have these two series, and I can combine them. So I get 8/9 n equals 0 to infinity 1 minus, or 1 plus negative 1 to the n plus 1 x over 3 to the n. And so you might say to yourself, okay, well, how in the world are those two things the same? Now, what you'll notice is that this is just some term. This is a geometric series, so it will still have the same interval of convergence, no problem. But what you see on this is that when n is an even number, this whole thing goes to 0, right? When n is equal to 0, this goes away. When n equals 1, however, this becomes like a 2, and so it adds together. So what you end up with is, when this is a 2, this becomes 16 over 9, and when it's a 0, it disappears. So you really only have the cases where n is even, or I'm sorry, where n is odd. Only in the cases where n is odd is this thing actually valid. So if I would, then what I have to do is I have to do some sort of separate indexing. Hold on. Should be in the case where n is even that it works. I've done something wrong. I've done something wrong, and that disappoints me. But the idea is still the same, and we could do something neat, because what you would want to do is you'd want to say, okay, well, k is 2n plus 1, so you're doing the odd cases. And then when you re-index this series, you actually get this. But again, this is the right way to do it. This is way, way faster. But the whole point of doing this is by setting you up for something very important. One, this we haven't really talked about, which is, what do you do when you have two series together? How do you How do you merge them? Well, it turns out that as long as they have the same indexing, like they start and end at the same index, you can actually just smash them together as long as they individually converge. And what you'll find here is that these individually converge on the same interval, so you can smash them together no problem, and you can do some really clever stuff to arrive at the same sort of thing, because you don't always have this nice clean format. Sometimes you do have to do things like this, which is just disappointing but true.